Okay, we're going to look at ionic bonding. This was a special request from Amy in Year 11 and I promised her we would cover it and I'd give her a shout out. So ionic bonding. First thing you need to recognise is that this is a bond between a metal and a non-metal. And if we're looking at the periodic table, we're looking at things on opposite sides of the table bonded together. Our classic example is sodium chloride, sodium and chlorine bonded together there. You need to be able to recognise, by being given any chemical, whether it's metal and non-metal bonded together, so ionic bonding, whether it's non-metal, which would be covalent bonding, or whether it's a metal by itself, which would be metallic bonding. The exam board expect you to be able to recognise that. If you can think of one example for the ionic and covalent in particular, that will help you remember those. So sodium chloride or table salt is our most famous ionic, and things like oxygen, carbon dioxide, methane are good covalent ones to think of when we're thinking simple covalent. Right, so metal, non-metal, we've got e.g. NaCl, and that's the example we're going to work through today. The other important thing to appreciate is that they form giant lattice structures, and that's going to be really significant when we start thinking about the properties that ionic substances have. Now, a lattice structure is basically a repeating pattern, and we basically got all these positive and negatively charged ions basically attracted to each other in a regular structure. Now, I've drawn a very simplistic 2D model here, and obviously you've seen ball and rod structures, models inside the classroom and in the lab, and they're obviously 3D. And we kind of look at them, they're quite small scale. Sodium chloride will be made up of millions, billions of atoms in this repeating pattern in all directions, okay? So that many bonds is going to affect its properties. Right, let's have a look at the different components. So let's start with the metals. This is the left side of the periodic table, which is significant. So we're thinking about group 1, 2 and 3 here. Now they have all got 1, 2 or 3 electrons in the outer shell, and they want to gain a full shell. So they want to have 8 electrons in their outer shell. So they could lose 1 or they could gain 7 or whatever might be their group number. And it's much easier to lose electrons. These ones will lose electrons. And so as a result they will become positive ions. Now if you get a little bit muddled about why this may happen, it is sometimes quite useful to draw out what's going on with the protons and the electrons. So we look at sodium. I'm just going to, you have a copy of the table, I'll just sketch out. So it's 2311 periodic table. It has 11 protons and they have a positive charge. 3, 4, 5, 6, 7, 8, 9, 10, 11. And they have 11 electrons because an atom does not have a charge. So these positive and negatives must balance out. When we ionically bond, the metal loses one of those electrons, and so all these ones cancel out, but we have a net positive charge there. Okay, and you can do this for the non-metals too and see the same pattern. Right, sodium has got 11 electrons. It's also in the third row, so I know it's going to have 3 shells. I'm just going to draw my little circle representing my shells or orbitals. And I'll do some crosses here. 1, 2, 3, 4. I've got 10. There's number 11. So it's got electron structure of 2, 8, 1. And we said it's going to lose the outer shell electron. So that's going to leave us with a sodium ion. And it's only going to have 2 shells now. Now, I now have electron structure of 2, 8, But we don't draw ions like this. We put brackets around it to show something's happened to it, and we write the charge outside the bracket, top corner, +1. Now you have a choice. You could write 1 plus, +1, or just put a plus sign there. Either is acceptable to the examiners, okay? But top upper corner on the right hand side, please. So we've got our sodium there. Now let's look at the non-metal side. Right, not all, I should have got a big bit of paper, but you get the idea. So non-metal, we're looking at groups 5, 6 or 7. They're going to gain electrons to form a full outer shell. So they form negative ions. So let's look at chlorine. Chlorine, if we take a bit of table, 35.5 because it has isotopes until 17. So chlorine, 1, 2, we're going to do circles this one, and that will come clear in a minute why. I've got 10 drilled so far, I need to do another 7, so I need one more ring. So that's our chlorine one. And you can see here, there's one space here which needs filling. And this electron that we lost from out here would be going to that chlorine there. So let's draw the ion. Circle. Now you may have noticed I am drawing these north, south, east, west, which I find prevents people from miscounting number of electrons. If you've got them drawn anywhere and everywhere on your orbitals, it's very easy to miss one out or put an extra one in. So if you draw north, south, east, west, that avoids that issue. Also, when you get to A-level chemistry, there's significance in electrons repelling each other. That's move on to A-level. But quite common in, I see as an examiner, people will miscount them when they do them anywhere. So do north, south, east, west, very easy to count, and you're less likely to make mistakes. But they will accept you put them anywhere on the orbital shell. So we've got an extra electron now, so it's going to be a -1 charge. So we've got our two ions. We've got a positive ion. This is just 288 now. This was 287. And we've got a negative one. And the key thing is, because they are oppositely charged, there is going to be electrostatic attraction. Electrostatic attraction. So basically, opposites attract. And that's a key bit lots of people miss out when they're doing exam questions. They quite often ask you to describe the bonding between a metal and a non-metal, and they'll give you an example to talk about. And there's a kind of checklist of things you need to consider. So we have a little think about that. Key things. Which elements are gaining or losing electrons? Is your first point. How many electrons are being gained or lost? Second point. What charge do those ions now have? Because they're no longer atoms, they've lost a gained electron, so they're ions. And where a lot of people miss out, they forget to write down that opposite charged ions are electrostatically attracted to each other. It's not always necessary, depending on how many marks the question is awarding, but this can potentially be a 5 or 6 mark question. And it's not actually a lengthy way to write this, because all we'd have to say is that sodium loses 1 electron to chlorine to form a N+ sodium ion, while the chlorine becomes a Cl- ion. They are electrostatically attracted. that kind of covers all those points. You can draw the diagrams, and sometimes they may ask you, and that's perfectly okay too. But key things to think about: what's going to lose electrons, how many they're losing, what charge they have, and don't forget to say they're electrostatically attracted, because if it's a 4 or 5 marker, they're looking for that last point in the end, and that is the most common thing that's left out. Right, properties of ionic bonding. So I said earlier that the lattice structure affects its properties. Now, with this lattice structure, we've got millions of positive and negative ions attracted to each other electrostatically. So, property-wise, we have got high melting points and boiling points. Okay, this is because there are so many electrostatic forces to overcome. And because there are so many, this is going to require lots of energy to overcome them. So if you think you try to melt salt on the Bunsen, you may have done the experiment class, it doesn't happen. You need to have hundreds, not 1,000 degrees Celsius, so we typically can't get that done over an ordinary Bunsen. The other property of ionic bonds is that they can conduct electricity in certain circumstances. Now, if they ever ask you a question about does something conduct electricity, they're looking for you to talk about free electrons or free ions, okay? This is the ionic bonding. So the electrons aren't free to move around. The electrons have been given a specific home. They are not delocalized. It's not going to be electrons, it's going to be ions, okay? So, when they are in this lattice structure we talked about earlier, they are not free to move. The only instance where the ions are free to move through the structure is when liquid or dissolved in water. And if you think about it, you can link this to C4 and electrolysis, that those substances that are involved in that typically are ionic. So only when liquid or dissolved in water, because charged ions need to be free to move throughout the structure carrying the charge. And the key bit there is it's ions, okay? It's not like in graphite, or it's not like in metallic bonding where they've got delocalized electrons. In this case, we've got charged ions that are free to move throughout the structure and carry the charge. Any question electricity, you're looking for the phrase carry the charge probably, and free to move throughout the structure. Right, that is a very brief overview of ionic bonding. Thanks to Amy for the suggestion. Any more suggestions, let me know in class.